不要给我关！
剪掉。
不要，等下还要贴。
为什么？这样子会好一点吗？你看他们讲很大声。
这是最后第二堂课。还有一个没有那个30不美，29不美，要多一个30。
啊？
这个没有 revision 课
？No。
你就把28写成29写成30。
这样就不美啊，这样更不美，中间空个洞。
那你就上了1个小时，另外1个小时就写29。
29是个 prime number。
对啊，就是不美啊，很丑你。卡在那边。
这样挺美的，20，这样挺美的，prime number。
以后人家27就还可以了。
我也会，27更丑。
27好过29。
No， 29。那你觉得为什么商场那些人每次报的都是29块钱？
那个是因为还要跟你讲少于30块，给人家做一种消费者。
哎，对，你们知道他们怎么放.99吗？
就是要让你有一个心理落差。比如说人家讲29块9毛9，那你就会讲哦少过30块。
没有，他们讲99就代表不可以再扣了。
真的，我以为
他们讲
要你买10个你就可以来。
我也是以前想。
没有，我一直以为讲999的目的是因为他要让你有一种少余的感觉。
我一直以为要按这个。
有一种看起来
上课
就给人一种写30跟写29研究。
报那个哪种？
你们猜就说
30一样。
这个是你自己的还是每个班？
自己。
哦，你自己的，这是你的。家里，家里，家里。很好奇，真的很大声吗？我真听不出来。
腊肠啊。
可是这是因为有一场来考试了，考试吃饭应该写 VQ， 那一道到升级，然后写那个。
什么叫你很聪明？什么叫聪明？哦，赵胜他讲你很聪明，赵胜。他讲你很聪明啊。你不是应该讲谢谢？
哦，谢谢。一个班长跟去另外一个班长。
看快点啊！你不是问我然后好，我都不觉得你今天昨天对美丽很好，出去了。不要过不掉。今
天教什么？今天教这个啊？咦，这么保密，怎么不弄这样子？
后来他们联络你了吗？啊？还在考虑。OK。他们有想他们要定成啥？他们有说他们要定成。
什么写好了？
这是上一届的。
哦，我以为现场写。
对啊，他上一届现场写的。今天要教的 High School University。
哦，又要来。
我这里一个太少。
那给我看，我没教错。 给我看，给我看，
你是去刚？
因为我很累，我要让我自己疯起来，我就精神一点了。但是可能有点太疯了。你要教这个High School University， 不是？
嗯。
这是什么？关于到我 ring 啊？
在总结看过了吗？
说 C 这是什么？这是什么？哦，这是我们做的 caution ring， 这是 caution。哦，caution 我们上学就学过啊。是的。
这个有没有学过？
哦，学过。
对。
discrete。Can we define a multiplicative coefficient of Asian coset？ 在哪里
我知道在哪。
？Define
就是那个什么之前的一个作业
OK，
就这个，这个一个是你之前说这个 y commute 的，
是我在做什么？不然明天都是假期。
真的，
真的，
对，这个我跟被刷进去。
圣诞节没有假期，读书啊。
他其实跟我说，就是我这个其实是在 prove 一个铁论，就是我把它写了出来，然后我去证明这个是 commute 的，然后这个写。
那你说给我看。我也是要看。
看吗？
有什么？
看吗？什么来的？
就是鱿鱼游戏。
哦，那个，我听到 split game。哦 ，sorry。去看哦，走，去看啊。快点走，这个半夜就去。你怎么
Netflix。
？Netflix。那明天，后天上映。
这个的话，因为我们
你拉是吧？
我们得到那个条件，normal，然后呢，我是用定义驱动，就是可能出现一个这个，就是因为 A B 等于 B 撇，就是它可能并不是说 A B 等于 B， 它可能是另一个 B。
G 哈，怎么有 A G 是吗？那怎么呢？怎么你用 A 不是 G 呗？
不是，首先我是得到这个 GN5， 然后一个是 N5G。
为什么这个是 A 不是 G 的？
因为我们出示这个，因为这个，
看
它是个容母差别，所以说对于y element G，GN5 equals to N5G， 然后呢 we choose B is in G5，
对
，so it must be is the element in N5 such as A B 等于 B equals to B prime A。
我是说 Seng 这边嘛，Seng 这个推出来的这个不是 GB 等于 B prime G，G 不是被选定了，G 被选定了。
I choose A in G。A
in G，A
in G。
但是这个 G 是小 G 哦。
对，我送完了，去米兰。
我知道
，choose element。
这个呢？这个 A 呢？
这个 A。我当时怎么想的？有点时间。
我的意思是说，你已经选定了一个 A 已经选定这个 G 了。这应该是 G。
应该 G 吧？
对
，GB 反正 G。然后呢 ，we use 就是这个是因为 N3 是 normal， 然后得出这个结果。对。然后呢，因为 N5 是 normal， 我再用那个，然后我得出了这样一个 equation。
这个不是也就 GC 可能等于 C prime G 哦？然后怎么
A 和 A prime？ 然后之前我是得出了一个叫，
所以
然后呢是 A B 可能等于 A prime A， 然后呢根据这边就可以等于 A prime
OK， 但是我现在就说这个是 G，OK， 假设是 G，然后这个拿到 GC 等于 C prime G 嘛，然后
然后的话，
前面大交叉点。
A B A prime。
哦，是这样。我讨厌
这里A B 应该是对 A prime B prime，因为 B prime 这边有 N5，我们得出这个 B prime A equals to A prime B prime， 然后前面又得出一个 A B equals to B prime A。
但是我是说，就
没事
啊，也对，没有是说 like，这一个推出 G B B prime G 嘛，然后你之后呢怎么推呢？之后，
然后这里的话，因为可以得出来，就是是因为 N5 它是 N5 也是一个 normal 上，这个 B in N5， 然后 legacy element。
可是这个 B 跟这个 B 就不一定一样。我的 B 是在 N5 里面还是在 N3 里面？怎么你 choose B 在 N5， 但是这个 B 出现在 N3？
这里，这边我确实这个多写了，不是 choose， 就是说这里的 B 跟那个 B 是一样的。
为什么 N3 的 B 跟 N5 的 B 不一样？你看，B 在 N5 啊，为什么这个 B 出现在 N3？你可以试下重新再写一次。
这里，因为当时我知道就是方老师用用 isobolics 嘛，我当时就尝试用这个证明，然后讨论了，然后可能他也没看出来，对。然后我这边，所以说这边一些我得出了这个 AB commute， 有可能这块，因为这块我其实就证明的定理可能就写错。
对，你可能要重新写一下。
然后这个是我写错。
OK，
这个我就是得出一个等式了。对，我其实意思就是写这个，我当时自己写的时候记错。
Division algorithm。
division。
对，除非你能够得到他们 commute 先，你才看这样子。你看你里面，你后面还真到里面只有一个东西。等你这个 B 呢，你就不那么随意的。其实就是 identity 嘛。
我可不可以 choose 它是一个 intersection？
对啊，我说你可以 choose， 但是你看你后面自己真到 M3 跟 N5 的 intersection 是1。这样的意思是说什么？其实就是 identity 啊。因为两边一定要有 identity 嘛。所以你选的东西其实就是 identity。那如果是 identity 的话，这个 equation 不是就很简单？
选 identity，
你只能够选到 identity， 而是说你用你后面证的。
那如果前面证的时候，我是不知道它是 identity
啊？对，
我去证明它是 identity。
你有用到那个条件证？你好像只用这个条件证诶。这边好像这一整段跟上面没有关系耶。
这边的话，我前面是得到
你得到你这一句，好像从这里吧，这里到这里跟前面没有关系。
我这边是想说，就是
对啊，
因为他们一个等于一。
对啊，你不是说这段跟前面没有关系？
跟前面是。
对，你把前面擦掉，这段还是对的。
对，就是这一段，这一段
跟这段没有关系，可能跟之后有关系吧。有，但是
这一段好像
再看看，
它这个 B prime 的 -1， 它这个equal to N5， 然后呢，我其实自己得到一个结论，然后呢，我们再用这个去推，
有没？
嗯，
没有吧？你看，你是看它的数量嘛，然后
嗯
看它的 intersection 嘛，
嗯
因为它是 subgroup 嘛，
嗯
然后 coprime，然后得出这个，
嗯
所以就跟前面没有关系啊，可能你 hence 之后要吧，但是 hence 之前是不用的。
哦
所以是说，如果你假设你把这段搬去前面的话，其实你选的东西也就是 identity 啊，对不对
identity 啊，
有啊，
想一下，
我自己查。
对，如果你要同时让 B 在 N5跟 N3在里面，肯定只有 identity 的。这题几分？
这题我有点忘了，
哦，
我之前是给我洗的。
OK，
所以
总分几分？我也忘记扣几分了。
10分，所以你给了几分？17分。
我是3分吧。
前面的我其实不是想说这个，我想说左边的 imply，右边的就是假如说这个条件，然后得出这个句是这样一个。对对，我不是说这几个句都是一样，就是我可能没写清楚吧。
你是 subgroup，
对，其实就相当于if len， 我就写个 implies。
哦，OK，但是我还是需要你来，写多一点来，怎么看到这些东西？
我知道，这个确实。
可以吧？看欺负。这个为什么？
哦，这个
不知道为什么写这句话出来。
这个我是因为我看到之前那个，
可是element S3
应该说它 subjective。I
mean S3 S3 确实是 S4 的一个 subgroup 啊。
是
啊，有什么用处在这里？
也就是说，讲错就是这 phi 是 subjective，然后才得出phi g 等于这个，然后非律句。因为对于每个句子有 C 个句音句 such that phi g goes to G， 就是 subjective 就是之前讲的。phi subjective
G prime G prime G prime
is
小 G 啊，小 G 也是大 G，大 G 是什么？大 G 是subgroup。subgroup 等于一个 element。
这是一个 set。
对，一个 set。
对，
所以小 G 是一个 set。
对，我是说一个就是对于每个几何都可能都要找到一个 G， 然后呢 ，the phi of G is a set，
但是跟这个什么关系？什么关系？
我讲说这个 P 是属于 S4 的，然后这个又是属于 S3 的。
对，但是这句话有什么关系？我看不出为什么要说这句话。我知道你说什么，但是我不知道是为什么这句话被放进。
这个我当时应该说是 subjective。
subjective。但是跟 infer 什么关系？
对，这个 infer 是。我当时是不应该写。
是吗？这样子够严谨。 好了，这样写作业大概这样。等一下，等下再看。OK， 要开始啊。OK， 那开始。啊，要开始。已经7点。OK，要进去。
确实可能就是对表达不是那个意思，但是我写出来就是错了。对。对，所以说这句话确实是有错误的。对，然后这里表达意思不是说他们记都是一样的，我是表示一个 implies， 就是应该说 if。
明白。OK，我看到了这边对，
然后这边我就是少了一点分析这样。
但是你的 hash 就很难看啊，就是很难读，我是说很难读。
对，我想说的是这个，
你应该要设不同的 hash 吧 ，hash 1 hash 2 hash 3 hash 4。呀，很难读。所以除非你设立不同的 hash i 你设6个 hash i hash 1 hash 2 hash 3那6个 hash
6个
hash 你有6个 hash i 嘛？
就这6个就 hash。
对啊，6个，你就设6个咯，不然的话很难读。对吧？可以帮我开关灯吗？啊，不要关灯啊！今天不要关灯。哎，不要！
我就说下次我还写这个H1等于这样。
对，比较容易。
是不快。
我先开始哦。
行。
你想一下，然后你再。哎，有声音吗？有啊，有声音。Hello, can everyone hear? 不太好，听得到吗 ？Can everyone hear? Can hear 吗？可以听到吗？好的 ，OK， 就这样吧，我们要结束了，反正。There's 2 more lecture to go. We almost finished our syllabus already. Okay, let's make a summary what we have did for last week, where we stopped. So I want to go in levels. So in your secondary school, right, what did you learn? You learn pretty much integer, right? Okay, and you learn divisibility. Okay, you know how to divide 2 numbers. And once you divide 2 numbers, you can use your division algorithm. Okay, whether it really divides it or will have some remainder left over. But you make sure that this remainder is strictly less than the A. A is the number that you're going to divide your integer. And another thing about division is GCD. Okay, so what's a GCD between 2 numbers here? Okay, since we have learned group, we just use group language to describe GCD. Okay, so if you look at the subgroup generated by this GCD of AB, what is it? It is all the linear combination of A and B. Okay, so this is what we have proven last time. So after you learn group, we learn rings. Okay, so let's go to a university level. So we learn polynomial rings. Okay. So polynomial rings, the coefficient is very important here. So you need to know over what ring, what coefficient you can use. And in this ring, right, you can also do division. Okay, you can also divide 2 polynomials such that your f is more monic here. So monic means what? The leading coefficient must be 1. Okay, only then you can do division. Similarly, you can have division with remainder also. So what do you remain here? So the degree of your remainder polynomial must be strictly less than the degree of f, the function that you take to divide. Okay. And we also have GCD ideas here, right? So when your ring is a field, okay, when your ring is a field, then you also can write what? RD equals to RF plus RG. Okay. So there exists a monic polynomial D for any two polynomial F and G. Okay. Okay. Can you see? Okay, both sides we can do similar stuff, division with remainder, and then we can find GCD. All right, let's go a bit deeper a bit. So in first year, you learn modular arithmetic, right? Z mod and Z. Okay, Z mod and Z. What can you do with Z mod and Z? First, you know that there are how many elements here? There's only n elements here. Okay, and you know how to add two numbers in Z mod and Z together. Okay, so A plus B mod n is equals to A mod n plus B mod n. And also, you know how to multiply two elements in Z mod and Z together also. A dot B mod n equals to A mod n times B mod n. Okay, just last week. Okay, so we almost end our section already. So what did you learn? You learned polynomial ring modeled by the ideal. Okay, a principal ideal. Okay, such that this this function has a root, call it alpha. Okay, and let's say it has a degree 0. Degree n. And maybe you want monic also. F monic. And we learn a phrase, right? Call adjoin an element to a ring. Okay, so let's say we have this isomorphism here. Okay, we model by a function. Then maybe we can build. So we need to build this isomorphism to where? To R adjoin alpha. Okay, such that F alpha equals to 0. So what's the prototype here? What's the prototype? You must remember the prototype. So what's the prototype here? Is the complex number. Okay, so the prototype is this. Rx multiplied by x squared plus 1 is isomorphic to R adjoin I, which is just C, complex number. Okay, so well, I mean, yeah. So this is how we introduce I. Okay, this is how we introduce I. So I mean, you ask you a question. So x squared plus 1, can you find a root or not? There a root. X squared plus 1 equals to 0. X squared plus 1 won't be equal to 0, right? Because x squared is always non-negative. Okay, non-negative. So non-negative number plus 1 is greater or equals to 1. Cannot be equal to 0. Okay, so to solve this problem, we add in this I by force. Okay, force it. Force the square of I equals to minus 1. Okay, so it's not real number. Okay, we just put this number in by force. And in this ring, right, we can do what? Well, before that, we know that this ring has basis, right? What's the basis of this ring? It also spanned by n element, okay, which is 1 alpha square up to alpha n minus 1. Okay, so what's this n come from? This n come from the degree of f. Why? Because if your degree is degree n, meaning what? Your f looks like alpha, x to the n plus maybe a n minus 1, x minus s to the n minus 1 up to a0. Okay, so if you let this function equal to 0, meaning what? you can express alpha n in terms of 1 up to alpha n. And on still remember the calculation, we can reduce alpha n using that function. Okay, so you can see that on the left hand side, you have n element, but right hand side, maybe you have infinite elements, but the basis is n element. Okay, the basis is n element. Okay, no. Although we go to infinite world, but the basis is still n. Okay, the number of bases. Yeah, no. Okay, so this is a difference. This is also a difference between finite set and vector space. Okay, finite dimensional vector space. So in finite dimensional vector space, for example, R. Okay, R, what's the dimension of R? What's the dimension of R? What's the basis in R? What's the basis in R? What's the basis in R? 1000. What's the basis in R? Huh? Basis in R? 1. Huh? 1. Yeah, real number. Okay, 1. You can use 1 to build every real number. Okay, it's linear combination of 1. Multiple of 1. Okay, so real number is dimension 1. But real number, what's the size of real number? Infinite. Okay. Okay, so if you compare it to finite set with one element, there's only one element there. Okay, so similar here. Here is finite set. There may be infinite, but basis only has n element. Okay. And so similarly here, we can also add, right? Okay, we can also add two polynomial together. Okay, let's say P alpha plus Q alpha. And here we also can do similar thing called mod the ideal of F. Okay, so what does it mean by mod an ideal of F? How do you understand this mod here? How do you understand this mod here? Still remember the calculation we did last time? After we add, right, maybe you have degree more than n, then you try to reduce the degree greater than n polynomial, right, to a less degree. You do what? Long division, for example. Okay. But how to understand this mod? This mod is actually the coset language. Okay, this is the coset language, meaning what? P alpha plus Q alpha. The coset of P alpha plus Q alpha is equal to what? Equals to the coset P alpha plus I plus Q alpha plus I. Okay, similarly, you can do multiplication. P alpha Q alpha plus I is equals to what? P alpha plus I times Q alpha plus I. Remember, this is what we define. It's not equal as a set. Then you can translate to the mod language. P alpha Q alpha mod out by the ideal generated by F is equals to P alpha mod out by F times Q alpha mod F. Okay, so what does it mean? So this means that we introduce a new language of coset. Okay, so introduce a new language of coset to describe this kind of modular arithmetic. Okay, so we have to replace modular arithmetic with a general ideal. Okay, no? Okay. Okay. Any question? Okay, so we are trying to generalize what we did before, okay, in a more sophisticated language. Okay, so one thing I want to emphasize here, this isomorphism here is not always true. What do I mean by not always true here? It doesn't say that if it doesn't say that. Let me put here. So warning. So it doesn't say that if f alpha equals 0, then R adjoint X mod out by alpha must be isomorphic to R adjoint alpha. This is not always true. Okay, this is not implied. It just says that if you have this as this, okay, then there's this string extension here. So let me give you an example. Yeah, let me give you an example. Okay, so I want to say that this is false. Okay, so this statement is false. Oh, thank you. Okay, so this is false. So let me give you a counter example here. So what counter example can I give you? So let's consider smaller ring. Okay, so when I want to build smaller ring, obviously I need a smaller coefficient. So what's the smallest coefficient I can play around? That's non-trivial. Maybe Z mod 2. Okay, and let's say Z mod 2 adjoint X. And in Z mod 2, okay, in Z mod 2, X squared plus 1 and X plus 1 has the same root. Okay, X squared plus 1 and X plus 1 has the same root. What's the root? What's the root for S squared plus 1? What's the root for S plus 1? 1. Right. So if you sub X equals to 1, 1 squared plus 1, 2, 1 plus 1, 2, so 0 in mod 2. Okay. So my claim is Z mod 2 adjoint X mod out by S squared plus 1 is not isomorphic to Z mod 2 adjoint X mod out by X plus 1. Okay. It's not true. Okay. Only one side is isomorphic to Z2. Okay, I mean Z2 adjoint 1, which is Z2. Okay. Yeah. Why? Why? So if you're isomorphic to Z2, meaning what? Isomorphic means what? Homomorphism and bijective. So meaning there are only two things there. Okay, only two things there. So how many things here? How many things is in here? 4. Okay, how to find the 4 things? How to find the 4 things here? How to find the 4 things here? So inside here, who is equals to 0? S squared plus 1 and all the multiple of S squared plus 1 is equals to the, is in the 0 coset. Okay, so inside here, you have the 0 coset. And then what else? Okay, before that, maybe give you some context. Inside Z squared adjoint X, what is in here? What are the degree 0 polynomial inside here? 1 and 0. Degree 1, X, and then X plus 1, and then, okay, degree 2, S squared, and then S squared plus 1, and then S squared plus X, and then S squared plus X plus 1, and then S cubed, and so on. Okay. So, but if you mod out by S squared plus 1, meaning what? You treat S squared plus 1 and 0 live in the same equivalent class. Yeah, no? Okay. And then what else? You also have 1 plus X squared plus 1. You also have X plus X squared plus 1. And then X plus 1 plus X squared plus 1. Do you still have X squared plus X squared plus 1 or not? Why no? Because I can write it as 1 plus x squared plus 1. Why? Why these two cosets is the same? You need to use the TFAE theorem, right? So what's the TFAE theorem here? S squared minus 1 equals to S squared plus 1, which live inside the ideal generated by S squared plus 1. Okay, so their difference live in the same ideal. So they should live in the same coset. Okay, this is the TFAE, right? Do you remember the TFAE? Okay, G inverse H live inside the normal subgroup implies what? H live in the same coset of G. Okay, you can prove it for ideal also. Okay, you can prove it for ideal. Okay. But how do you do this calculation? You also can use the long division, right? Also, you can use long division to do it. Okay, because if you take x squared divided by x squared plus 1, what do you get? So meaning what? Meaning x squared equals to s squared plus 1 plus 1. Okay, so you see, remainder and the function live in the same coset. What you do here, right? First here, who live in the same coset? All numbers that have the same remainder. Correct or not? All the numbers that have the same remainder live in the same coset. For example, what? Let's say MAT211. You know MAT211, right? Every day you need to look at the clock. So who live in the same coset with 13? 1. Why? If you divide 1 by 12, you get 1 remainder. You divide 13 with 12, you get 1 remainder. What else? 25. Also live in the same coset of 13 because you divide by 12, you get 1 remainder. Okay, so it's the same. Okay, it's the same logic here. Okay, so actually, how many things here? Actually, you can prove that. So we already proved that. There are actually 4 things here. But on the other side, there's only 2 things. Okay, so one side got 4, one side got 2. You can't build a bijection. Okay, no need to talk about isomorphism already. I mean homomorphism. There's no bijection. Okay. Does it make sense? Okay, one has more things, one has less things, so there's no bijection. Biject meaning both sides have to have the same number of elements. Okay. If you have a bijection, then both sides have the same. So I include this as your in the last lecture already. Just that I want to mention it to you. Okay, any question? So far, any question? Okay. If no question, let's go to product ring. So product ring is pretty important. I include it in your exam. I think this is the one last thing I add in your exam. Yeah. There's a very important result that I want you to remember. Okay, because this fact is always used in at least my research, at least my research area. Okay, later I will introduce it to you. So before that, let's introduce what is a product ring. So actually, product ring is pretty similar to product group. Okay, so in that case, we will test 加零 again. Right, last time we test 加零, right? So how should we define LOC on let's say R cross R prime? Okay. See if 加零 can get it right this time. So how should we define addition and multiplication for product ring? 来，上次是还加零，对不对？这次也是还加零啊。So how do we define addition and multiplication? 怎么样？ What do you think? 不要偷看答案。好，你写。If you know you have two rings, then how do you combine them? 啊？加起来。对啊，我就问你讲加起来。我加起来。Okay, so I mean, wait. So let's say we have x prime, and then y prime here. So how should I define this addition here? So first addition happened in where? First addition happened in where? R. Second addition happened in R prime. Okay. So multiplication. X dot y in R and x prime dot y prime in R prime. So what do we call this way if we define this way? This is called what? Component wise. Okay, we add component wise. Okay. We add and multiply components wise. Okay, no? Okay. So in this case here, what is the additive identity here? What's the additive identity? Huh? What's the additive identity? Huh? It's what, 0? Origin? Here don't have origin. Here no R2. So what do you put on the first spot? 0 in kosong. Wow, you know kosong. Wow, 厉害. Kosong R and kosong prime. Kosong R prime. Okay, kosong. 很好诶，有录像随时。How about multiplicative identity? Hmm? 是什么？1, good. 1 R and 1 R prime. Okay, 非常好，没白学。Okay. Right. Okay. Very trivial, huh? Sorry? 什么？什么叫 scalar multiplication？ 你说要 define 啊？没有啊，没有啊，没有啊。Ring inside ring we only have vector addition, vector multiplication. No scalar. No scalar. Yeah, there's no scalar here. Yeah. Later I will introduce some structure that have scalar multiplication. But now we only have, yeah, that's called module. Now we only have ring. Rings means what? 2 LLC. One LLC is addition and multiplication. And then these two operations happen within the same set. Scalar multiplication happen outside the set. Scalar live in different world. Later we'll talk about this before we end this course. And C. So whenever we talk about products, we'll learn about projection. Okay, projection. Projections meaning we just look at one of the factor. Okay, we can project to two places, right? We can either project to R or we can project to R prime. Okay, so maybe we take x prime and then we get x prime, or we take x prime, we project to, first one we project to x, second one we project to, and then you should prove that these form a ring homomorphism. Okay, very good exercise to do. Ring homomorphism. And then what's the kernel? What do you think? What's the kernel of the two projection? Kernel of pi is what? What's the kernel? What are the things that get sent to 0? Huh? 0 cross everything in R prime. Okay. 0 cross everything in R prime. Yeah, no? Okay. How about kernel of pi prime? R cross 0. Only on one summon, on one factor, there's only 0 gets squared, and then you can put everything. Okay. All right. And what else you can prove? Actually, you can prove that you can prove what? You can prove that actually these two form a ring. Where they're actually a ring also. Their kernel is a ring. What's the if it is a ring, right? We can talk about multiplicative identity. So what's the multiplicative identity on both sides? What's the multiplicative identity here? Or what are the multiplicative identity? E? What E? What's the multiplicative identity here? Sorry? E turn R prime? You mean like this? But on this side, you only have 0. So this, the first coordinate here must be 0. 0, comma what? 1. Okay, 0, comma 1. Okay, you imagine, is it correct or not? If I have 0, comma R prime multiply with 0, comma 1, do you get 0, comma R prime? Right. Okay. Second, what's the identity here? 1, comma 0. Okay, so you check. Okay, it forms a multiplicative identity. Okay. So far, okay. Okay 吗？很简单是吗？很简单啊。Okay. Next, we'll define the thing. So we won't we won't prove everything here. You can go back and prove it. So next, an idempotent. Okay, so idempotent is a very important object in research. So what is an idempotent here? So idempotent element E of a ring, let's call the ring X, is an element of X such that it satisfies this property here. E square equals to E. Okay, E square equals to E. So for example, let's give an example here. In Z6, can you find any idempotent or not? Something that square to itself. Z6 only have 6 elements. Go and try it. Okay. 再等多1分钟. What's the element that squares to itself? Huh? E, right? E is also one idempotent. E is always an idempotent, right? Huh? 3. 3 what? 3 square equals to what? 9. 9 equals to 3 mod 6. Okay. Yeah, identity is always an idempotent. Okay, but it could be other idempotent. Second, in linear algebra, what did you learn? You learn projection. Okay. Or maybe you have orthogonal projection. If you do orthogonal projection twice, okay, it is the same projection. You do it twice, you still get the same thing. Correct or not? After you project, already go into the plane. You project again, still in that plane. Yeah. So actually, this is a motivation. Actually, the real motivation. We try to project to somewhere using this idempotent. Okay, project into some places. Okay, so this theorem is very important for your exam. So what's this theorem here? Let X be a ring and E be an idempotent. We can write X isomorphic to E times X cross 1 minus E times X. Okay. So we try to use idempotent to split our ring. Okay. So this isomorphism here is a ring isomorphism. Okay, it's a ring isomorphism. Okay. So to produce this ring isomorphism, right, you need to tell me a map. Okay, you need to tell me a map, right, and then show what? The map is surjective and injective. Go back to first part of the course. Okay. Produce the map. So I give you let you think. So what do you think? What's the tuple you need to send to? I mean, a natural way to define it. We should start with the most natural way first. Okay. What can you do? 如果你不爱，你可以试一下，不要勉强啊。不要勉强。So X, how to go to EX cross 1 minus EX? Where do you send the elements to? What's the natural way to map here? What's the natural way? Huh? Send to where? Send to what tuple here? 什么？招生你要讲吗 ？S 降 X 啊？另外一边呢？这样子 SS。这样你不是很小看这个 E 啊 ？EX yeah。另外一边呢？我们see yeah try the obvious thing first 吗 ？Okay or not? Try the most obvious thing first. Okay, so let's try if this work or not. Okay, let's try if this work or not. Okay. So let's. How many things to check here? One, ring homomorphism. And then injective and surjective. Okay, let's try. Okay, so ring homomorphism, what do we need to do? 3 things to check, right? 3 things to check. So for every U and V in X, what do you need to show? Let's call it phi then. So phi of U plus V equals to phi U plus phi V. And then phi U times V equals to phi U phi V. And then you need to check that phi identity gets sent to identity. Okay, identity in both case. How to write this? So identity of EX cross 1 minus EX. Good. Okay. All right. So let's check which one first. Okay. So what do we do here? So what do we do here? What should we do here? 哎，不然庞鑫来做一下，来庞鑫，做，试下能不能 pro？ 是啊，来试轮流，不是来做一下，很简单，不是来做一下，做一下，做一下，哎，来做一下。我们有摸鼻子吗？哎，看一下。
那你要加浓吗？
是，看，别放，别放。全部人 try 啊，全部人 try。哦，没有 try。
救了，
try 一下。
要起救了。
不能 try 啊，你先 try 救吧。
这样。哎。
Everyone try 啊 ，try together。try together 啊 ，take out your pen。
吓死我！我刚才玩电话。小丽人。哎。
不错。
嗯。
OK， 不要走先，不要这样快走。OK， 不错。
今天是有答案的。
哪里答哪里？有没？你有看到答案没？没有啊，没有答案。乘法呢，也做做看。把这个拉下去。
可以。
OK， 你做。来，今天有庞鑫小老师。
是啊。有病啊你！
来 do together 啊 ，please do。
想想。我不，这说到我不是从来没 proof 的那，我等我直接。从来没有醒过。
Yeah, there's some technique involved here already, but what can you do? Does it come here or not?
Is it the Nikki? Chana is scared.
Yeah, I'll read it from there. Let's go from here. When E from here.
Identity.
And E is identity is not an identity, right? It's just an idempotent.
Someone has from you?
Yeah.
Someone?
The ring that we consider is what? Commutative. Meaning what? Multiplication is always
Commutative. 什么？你讲什么？
ring. The ring we consider is always commutative.
multiplication. Okay. Next one.
不懂是 isomerism，然后我 define
老师你
define 咩？哪里？
老师教我们的。
哦
Yeah, the ring that we consider is just
咁
have commutative multiplication. Okay, so you can compute that. Continue.
UV EUV 啊，
Why?
因为 idempotent
Because idempotent, yes. Okay, how about the other side? Why?
S
Can you calculate for us?
OK，
What is E minus 1 minus
喂
2?
你还可以加白的，
我没有 set.
看 Mickey Mouse，要沉进去吗？喂，哦，减一，好，
Okay, good, very good. Okay, 继续。
骗人的
Put the last one. Then I let you go.
gamer，
By 1 equals to. Yeah, I'll
等一下我不会，我会ES， 我去啊，一减，哎不对，哎一除以一，
And then, how do you get it?
什么？
How do you get the end? Yeah. What is E times 1?
1
Huh? E times 1 equals to 1? You sure?
no， 1是什么？我 stress 哎，
What is the multiplicative identity? So anything you multiply to 1, you get.
哎，
And then, so the question is whether E comma 1 minus E is the identity in EX cross 1 minus EX or not. Is it true? If you take everything in EX, take anything from EX,
写在哪里？
在旁边
有什么？
take anything from EX. Take anything from EX.
两写，6啊，还是 for all？
Any K-N-Y. K-E-E 小 x
什么？你 S E S
大 x
S
EX EX. Okay. No. ES is EX. ES is EX.
哦，要还是写错？
Okay. So what is ES times E? What's ES times E? ES times E is what?
Yes，
Right now? Right now. EX times X equals to. Sorry. EX times E. Okay. Also, E times EX is also EX. Element in 1 minus E times X. So take any.
什么？等一下，
So do the other identity already.
Oh.
Next identity. So take any 1 minus E X in 1 minus E big X. Can you try to compute? Yes. Okay.
很小的 iPad。1减1 square 跟上面一样。1减。
Yeah, 三跟一样。So 三跟一样 means what? If E is an idempotent, 1 minus E is also an idempotent. Then D minus the idempotent still an idempotent. You are not so important here. Then you take multiplicative identity minus the idempotent is still an idempotent. Okay? Yeah, very good. Hey, BL.
他们是最好出这题哦。
啊，我最好出，我最好出，我出你就请我吃饭是不是？真的真的，全部都要请我吃饭。Okay, okay. So before, 你们要结束掉这个 proof 吗？还是你们要休息？要上厕所。Okay, how about we take a break？ 我们回来继续 proof injective 的这点。跑上去。check， 要 check 它是不是个 identity。
你知道不是这个是 identity 我懂，他是要 check 这两个东西是 identity 不是？
对啊，在这里面的。1只是1 square 等于1吧？
这样做是吗？
怎样做？
我们这个是从这个来的，或者
对啊对啊，其实你要把它搬下来。
对，我就体会我的手袋。
好。
你该讲ว่า and 该讲ว่า and what I don't order
给你开，
然后我
开了，
哦，
来给你开。
1如果是 idempotent， 1减
1也是 idempotent，
这个是 multiplicative。谁打我？哎，吃啊，给他们吃啊，他们有披萨，
他们力量买了，然后力量给我，
那很多。1是 idempotent， 1减1就是一个，就是这个计算。
不是开这样。
我去年的课件写了4个命题的，你今年只有1个，
因为我觉得会模糊焦点，如果把那4个写出来。
打的是打4个，打1个，
打4个，
那就好。因为你刚刚讲6的时候，我觉得帮你打。
打4。
因为我没跟他们说我上次我。
对，就这样呀，
我上午帮你听。
一样。是啊。
我还没有认真想你在讲，我还没有认真想你在讲。
这需要认真想吗？你想就行，你不用想，你都知道了。你就没发现你这节课讲的东西已经跟这句话违背了？
我发现这呲牙咧嘴。
上次说一个 subring 就是一个 subset of a ring， 下题词反应 all ring axioms， 但是这节课很多东西已经帮你看到了，就算它 satisfy all ring axioms， 它也不一定是 subring。ES 就是一个例子啊。
有当时候在想这句话的时候，其实我有想说那个 multiplicative identity 要从原本的变来。
对。
OK， 加这个，
只要加这个条件。
公共。
吃拿去吃啊，拿去分。拿去分给他们吃啊。放给他们吃。
我这个。
OK。
对吧？就是感觉好像就是写的不很好，好像感觉不老死。
我没有说你说啊，我是说你写不够吧？没有写你就，我是觉得你写不够吧？
就是我在扣，
因为我扣的是我不知道你知不知道这些东西存在了，你怎么去检查呢？不知道。然后第二个是知道你知不知道它已经完整了， 然后它是不是个 sub？这些问题哦，要出。
这个是差不多，这个我的前面就有说。
Yeah， 这个我知道，但是我是说来找出来的 inverse image，他们为什么是 subgroup， 然后为什么已经足够了，完整了？为什么他们会 generate 这整个 subgroup？然后你怎么看到的这个？怎么找到这些答案？我是扣这些地方。
看回这个。就是喜欢找那真是对，然后
是一个比较久远的。
对。
用的方法
所以的，所以他现在在赢这个 case 的话，他的一是 identity， 一节一也是 identity。他本身也是，他就关掉这两个，在这个 case 表一是 identity， 在这个 case 表
除以 fx 的 ideal 不等于 RA 的时候，是不是因为它有 multiple repeated loops？
其中一个原因，如果你要讲的话，其实就是 irreducible。
一定要是 irreducible 才可以，那个才会想到。
对，但是我们没有加 irreducible 概念，所以就不把这东西带进来。
可是我们要解 zx 是 x 平方加1，也不是要把它拉到 complex number 讲没有 irreducible 才能讲那个。
应该可以讨论在 zx
去到 z。I 的可能是 x 平方加1，这个不就是用到 irreducible 了吗？就是因为
对，I mean 我没有提这个概念嘛 ，I mean 我也没有用到那个 property， 我只是检查 element 罢了 ，Yeah， 因为没有介绍这个概念，所以就没有告诉你们什么情况下一定有这种东西或者没有。
就是那个。
对，确实在这个里面 ，x 加1乘 x 加1等于 x 平方加1。
对。irreducible
就是这个东西，他说不一定的，
上面睡的这个
不一定加。
好像说
等价的前提条件是 f(x) 的方法就是不能。
就是
它在这一个环里面，
这个
不能因式分解。
因为我自己有看到。
哦，因式分解的话，可以是拿这一个就做完，或者这一个就做完。
这是什么东西？
就是
假设反的，翻了可以。
你翻。
你呀，讲了嘛？我呀。OK， 等下顺便继续补。啊，可以啊，可以，这样你继续补。OK， 很好，非常好。
好像就没有。
会错。
真的。
你骗我，你请我吃饭啊
？OK， 如果我没有骗你，请我吃饭。
哦，分析这题。
你这个证明我是画从2年，他是 obvious 这概念，当时还没介绍，所以我就不能用。然后呢，所以说我才有这后面讲的这。对，就是它首先 define 一个 set 是一个元素 table， 然后 such that you want to OK 这个你发的，然后这边呢上x1， 然后跟点它们都确定了，那么 xp 就相当于 s 这样的，所以说 xp 它是 c， 你说 element a。
看一下讲 proof injective 就是那个我会 subjective 也是我会 for all subjective 是 for all y in 可以听就我先 for all y in 这里in 这里
对
and this 这里的东西 such that b 这个东西
不然等下再想一下
等于 b 的另外一个东西等于这个
等下再想一下
就是 b subjective
对
subjective 是
我觉得这个有点
有
点明
if v 这个等于 v
这个等于这个就等于这个 OK 我不要连你们两个是等于我准备好了 我用1×3看。
换你们的。就比如 if u 等于 v then v 等于 u 不是？
等于 u 等于 v。
u 等于 v 一样的啦。哦，左边右边不会调换是吗？
不美。
我懂了。然后呢，你看。
对，它是盗版。没有，你翻就是的款本。去年的。也
没有
小杨呢？小杨没有在，跟去年同年。红姐也没有在，子明呢？子明也没有在，子明在哪里哦？有人知道子明去哪里吗？不知道，都不知道。啊？没有来，知道为什么没有来吗？不知道。伟哲呢 ？OK。
哦，因为他丢给伟哲，走过去，他丢不掉。
曾子涵，哎，等一下我点名。子涵，曾子涵没有在。哦，在。OK。
自己啊。
林金在。
雨天在，小天不在，包车弟在。
金鱼呢？金鱼不懂。浩瑞。一晨 ，OK。心仪不在啊，心仪不在。何心仪不在。考试啊，做 assignment。哎，怎么？为什么他？修光不在啊。冰夏在吗？冰夏呢？冰夏呢？他干嘛？他什么？
偏头痛。
哦，偏头痛。OK。小叶在。常云在，延胜在，陈川在中，在，我心在。
对，再来。我在讲会中吗？应该不会吧。
Okay, I guess pretty much we will finish it by today for exam material. And if you care, maybe you can come to the last lecture and we will take a talk before we. 没有啦，怎么可以这么说呢？没有啦 ，OK 啦。Last lecture, what we will do is we will cover something. Actually, it's very important. Okay, but we have no chance to include it in the exam. 也不可以，因为那个东西有其他东西要讲。I want to introduce some advanced courses to you also. Yeah. Okay. Okay, not just our general topology, other stuff also. Other stuff. Yeah. How? Okay. So if you can inform your friend, we can take the class photo on Thursday. I thought we're gonna take today, but today is not full. Maybe Thursday also not full, but. Huh? OK， 韩星你要继续 prove 吗？来继续 prove 啊 ，prove。exercise。
写啊。
写啊。
这样啊，我忘记了，这样。
自己写啊，写在你自己，看下会不一样。
你记住我的位啊！不要。BAESEJ。
还要说中文是什么？ 讲密的密啊。
对，啊是吗？
这样啊？
接下来答案没你可以检查。算了，你继续算呗。
喂，陈喂，点什么？来的没？对，有对。这个觉得
Economize equal right？ EA 的你。
我这样啊。可以 cancel 吧 ？cancellation。
Can use cancellation law 呢？E got inverse or not? Ring 哦 ，ring 哪里有？
啊，没有。
如果有 inverse 不是 fail 了。So how? A 是 TFA。怎么办？剩下答案
没有。
这边。要 prove A equals to B right? Start with A 咯。
但就不要这边了。
没有，那个是对的，全部是对的。这边目前为止都是对的，继续吧。Start with A. A equals what?
这边。
Start. A. No, start with A.
A
equals what?
一乘 x。
No.
诶，哦，懂，一乘。
Then.
厉害了。
厉害哦。
对。
我犯错了哎。
没有啊。
谁？对。哦，Hello。哎，Hello。Hello。哦，OK，好。没有，我先写是。我犯错了哎。对。延伸说你犯错了。
对不起。
OK，然后。And then. And then. Hello, try and do 啊。
对啊。
算完了吧？
A 等于这个。
然后。
哦。
然后呢？
我真的是这个 A 等于 B。
你要 distribute B。
哦。
Okay. So you basically you split A into two parts, right? And then two parts is equal to the two parts of E, so equals to B. Subjectivity. What's the thing in X that sends to these two things? You live in EX, right? What do you need to prove? What is surjectivity? That exists, Can we call another name? W maybe? There exists a W in X such that phi of W equals to UV. So what's the W you should take? Surjectivity. Surjectivity 的 statement 是什么？ Yeah.
然后呢
Yeah.
B 的前面点后面。那我现在死亡这样乱呢？
写下来先。
There exists for 这个in，然后 there exists a UV。
前面是什么？你前面的 space 是什么？What's your domains？
domain 是这个 there exists a S。S in S such that B S 等于等啊？
没有啊，等于 UV 啊。Right. So what's S? What's the S you need to set here?
want to show that.
Yeah, you need to find the S given UV. Given UV, you need to find the S. Right? Calculate. Try 了。
怎么？
看一下能不能啊？
怎么你就知道
？Try 啊。
怎么？
算啊。Phi of U plus V 是吧？
怎么样知道？怎么会有这个东西？
猜啊，就来找它的 preimage， 能够算到 UV 为止。Right？
死掉了。U 加 V 是什么？U 加 V 这个加这个。
Phi what happened？
就这个。
Phi map is what？
这个。
哦。
因为我这个是 U 加 V 嘛。
对。
所以是 U 加 V 一减。
Yes。Okay. So what do you get?
存进去。
Yeah. So?
No.
Oh, the claim is this thing is equals to UV. Why? Claim is this is equal to UV. Okay, you haven't used the condition U is in EX, right? V is in 1 minus EX. You haven't used that condition yet. Okay, so how are we going to use that condition?
直接套。
套什么？不要再叫那个 S 啊，前面选哪一个 S 啊？叫其他 S，maybe S1。
我前面唱一个。
对啊。E live in where?
也是2。
What do you think? Maybe different 吗 Could be different. They could come from different axons. Why you get 0? Okay. 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 Okay.
Oh.
有算错吗？
应该算错。
这个 ES2是什么 ？1 minus ES2吧。这个 1 minus C V。
可以抽。
Yeah. Okay. Okay. Thank you. Okay. Good. Okay. Good. Very good. Yeah. So some things I want to note here. You see, if we write like this, isn't it confusing? Okay, so a bit confusing here. So make sure you write elsewhere. Or make sure you write elsewhere this calculation here. Okay. What did you notice in this calculation here? Actually, you use the fact that E times Y minus E is equals to 0. Okay, meaning what? Like dot product equals 0, right? Actually, these two is kind of orthogonal. Okay, these two things are orthogonal. So actually, you split your ring into two orthogonal rings. Okay, no? Yeah, so they kind of orthogonally decompose your ring. Okay, the idempotence. Okay. Okay, so let's go a quick example here. Okay, for example, just now we said that Z6 has an idempotent 3, right? So we can split Z6 into 3 times Z6 cross 1 minus 3 times Z6, which means what? 3 Z6 cross 4 Z6. But what does this mean? Can you identify exactly what are the elements inside here? What are the 6 elements inside here? Because on the other side tells you only 6, right? So how do you identify 6 things here? How do I identify? So in the first Z6, what do you do? Z6, what's the elements inside there? 0, 1, 2, 3, 4, 5. So everything you multiply by 3. Okay, so there are 0, 3, 6, 9, 12, 16. And remember that you want to mod by 6. On the other side, you multiply by 4. Okay. But if you multiply by 6, what's left on two sides? What's left here? Up to 6 is the same. 3, 0, 6 becomes 0. 9 equals to 3. 12, 0. 15, 3. So what left here is 0 and 3. Okay, so remember we multiply by 16. Multiply by 6. On the other side, mod 6 is the same. So 0, 4, 8, 8 is the same as 2. 12 is the same as 0. 16, 4, 30, 2, 24, 0. Okay, so what's left is 0, 2, and 4. So what's these two rings here? Actually, this two ring is Z2 cross Z3. Only 2 elements here, 3 elements. Okay. Okay, no. Okay, in group, we already have this kind of isomorphism, right? Remember, finally generated abelian group. Okay, we break them into the vectors. Okay, in this case, we also have breaking down the product, rings into product ring. Okay, so it's isomorphic as ring also. Okay, not just group. Okay, not. A question? Any question? Yes, 来。1.3 1.3 minus 2 in mod 6 is what? It's 4. Okay, yeah. Okay, no? Okay. All right, so last topic of the day, we'll talk about fraction. Okay, so let's form a fractions here. So I'm not using the natural number way. I'm using the natural number way to tell you. So the motivation is we want to learn about the fraction field of Z. Okay, so meaning we want to invert everything inside Z. If we invert everything inside Z multiplicatively, it is actually rational number. Okay, it's actually rational number. So what sort of property rational number has? A over B equals to C over D if AD equals to BC. Okay. I mean, in high school, maybe the teacher will tell you like cancel all the common factor, right? But this is what it means by canceling all the common factor. Okay, AD equals to BC. And how do you add two fractions together? You are asked to make the denominator the same first, and then also multiply the factor to your numerator, and then only then you add them together. Okay, only then you add them together. And how to multiply two fractions together? You just multiply the numerator together and denominator together. Okay, so why it works? Okay, you need to prove actually. Okay, you need to prove. So the question you can pose here is, you see, you divide by BD, right? Okay, so you usually require what? BD equals to, or BD cannot be equals to 0. Okay, but let's say we ask a question. If B is not 0, D is not 0, can BD become 0? Cannot, man? Cannot. Thousand said cannot. Can. Can, then you need to show me example. If B not 0, D not 0, why BD can go to 0? Huh? Anywhere, the ring we consider. Any ring we consider. Which ring will have that property? Mod. For example, what? Give an example. Huh? 什么？这边吗？都有了嘛，对不对？2 is not 0, 3 is not 0, but 2 times 3 equals to 0. Okay, mod 6. Okay, so if you consider that mod 6. So this kind of property that Z have is what we call a integral domain. Okay. So definition. And an integral domain. Okay, or sometimes we just call it a domain. okay, is a ring such that R is not zero ring. So I'll just say that R is not equals to zero ring. And if AB equals 0, then either A equals 0 or B equals 0. Okay, cannot have two non-zero things multiply to 0. Okay, this is what we call integral domain. So what kind of integral domain you have seen before? Sort of integral domain. What sort of integral domain? R, good. R2 also can. Z, C, or the field. Okay, polynomial ring. Okay. These are all integral domain. Okay. Any field. Oh, right. Then a bit dangerous, huh? Should we consider characteristic 0? Field of a characteristic 0. Field with characteristic 0 should be fine, right? So, do you remember what's the characteristic means? Characteristic 0. Okay. Characteristic 0. And a non-example is like what he's going to say, right? So non-example. Just now we gave a Z6, right? Or maybe F4. Not F4, F5, but 5 a few. Okay. Because in Z6, 2 times 3 equals to 0. Wait, let me think. So in field, do you have wait, in this thing, in this F5 here, any non-zero number multiplied to 0? I don't think so. I don't think so. I think field should be fine. Field is an integral domain. Can we prove it or not? Can I prove it? Every field should be an integral domain. F5, right? If you consider all the possible multiplication, you won't get 0. Can we prove that every field is an integral domain? How do we prove it? Obviously, every field is not a 0 ring. I think we can prove it right. Every field should be an integral domain. What? Right, so the thing we need to prove is if maybe I write here, claim let A be in field if A and B not 0, then AB is also not 0. Okay, can we prove it? Contradiction. Suppose for a contradiction. So prove. Suppose on the contrary, AB equals 0, then you can use cancellation law. So by cancellation law, what do you get? What do you get? A inverse AB equals to A inverse 0. You get B equals to 0 implies what? 1 equals to 0, which is a contradiction. Because once you get 1 equals 0 means what? You will get a 0 ring. But field is not a 0. Okay. Okay. 1. Okay. Yeah. So there's a contradiction here. Okay. So field is always a integral domain. All right, continue. Definition again. An integral domain in which every ideal is principal is called a principal ideal domain. I claim that you have seen principal ideal domain before. So what are the principal ideal domain? But through some statement, right? Ideal is generated by a single element, a monic polynomial. What are the rings here? For example, what? Z? Okay, and also the polynomial ring over a field. Okay, so these, the ideal in this ring, we have proven that it's always generated by a single element. Okay, what is the element that generates the ideal in Z? The smallest positive integer. In the polynomial ring over a field, the monic polynomial with the smallest positive degree. Okay, yeah. And proposition. There are some proposition. Maybe we don't want to go through the proof. So proposition. Any subring of a field is a domain. Okay, is a domain. Similar to what we did just now. So just now we proved for the whole field, right? Actually, you can prove for any subring of this field. It's a domain. It's an integral domain. And then if R is a integral domain, then if you consider the polynomial ring, okay, over this integral domain, is still an integral domain. Okay, it's still integral domain. So I think maybe this statement has something worth to discuss here. If you know that the coefficient, they are non-zero multiplied together, also non-zero, right? But the problem in R adjoint X means what? You have a monomial. Stick to your coefficient. So can X multiply X get to 0? No? Cannot, right? You just increase by power. Okay, so it's still an integral domain. Okay, no, you won't cancel out your coefficient. I mean, obviously you need to prove it. Let's skip it. So another thing is something called a zero divisor. Okay, so the zero divisor is pretty important here. So what do you think about zero divisor? The thing that can divide 0. The thing can divide 0. So if it is non-zero, and if there exists another non-zero b such that ab equals to 0. From here, can you see why we call A a zero divisor? You can play around with this equation, right? Maybe write it as b equals to 0 over a. A0 is nothing. You divide by a, you get something non-zero. Crazy. It's crazy. 你疯了。Okay. 零嘛，没有东西嘛，你 divide by something non-zero， 忽然间有东西。Right, crazy 了。And please don't write this in your exam. 不要写这个东西啊，这个我只是给你有印象嘛。This is what it is defined. Okay, because this doesn't make sense yet. Whoever defined it. Okay, no? Okay, you can memorize this, but write this down. AB equals 0. Two non-zero elements multiplied to 0. So if A is a zero divisor of 0, if A is a zero divisor, then B is also a zero divisor. Okay. So this one is a bit. In max, we say observe. Observe. Okay, observe. Observe 什么？疯狂。欢腾. Okay, 欢腾. Very good. Observe. All right. So proposition. 可以 link 吗？如果我有 zero divisor to integral domain， 怎样把这个两个 idea 连在一起 ？An integral domain is a what？ 什么有还是没有？有 zero divisor 还是没有 zero divisor？ 没有 ，which contain no zero divisor， 对吗？是不是没有 ？What happened in integral domain 啊 ？If a b equals 0, one of them must be 0。OK， 这两个是同时都不是零哦，突然间产出。Integral domain 是你要拿到零的话，其中一个一定要是零。OK，if a b equals 0, a is equal 0 or b is equal 0, one of them. Okay, so almost by definition, this proposition. And another proposition is a very good law, as this here, cancellation law. I think this is worth to prove. Okay, let's prove this one. If R is an integral domain, can actually use cancellation law. Okay, so meaning what? For every A, B, C in R, if A, B equal to AC and A not equal to B, 0, then B equals to C. Hey, you cannot use inverse here, huh? It's just a ring. So how to prove this? Huh? Can you think about it? 想一下. There's no inverse, huh? But somehow you can get B equal to C. How? How? Obviously, you start from AB equals to AC. Okay, so how do you get B equals to C? Cannot apply A inverse, no? This is a ring. Don't know inverse exists or not. But still, you can cancel the A. How? Any trick you can play here? Huh? Mention your try, ma? Huh? Okay, you can take the additive inverse of AC. And then you can use distributivity, right, in the ring. So you get A times B plus minus C equals to 0. Then, and what? Huh? When I divide A, I haven't defined divide for you. But R is an integral domain, right? Two elements multiply equals 0, meaning what? Either A is 0 or B plus minus C is 0. But we have A is not 0. This means that B plus minus C is 0. Okay, so this implies that B plus minus C is 0 since R is integral domain, is an integral domain, and A is not 0. So this implies that B equals to C. Yeah. So this means what? Integral domain is kind of a substitute for your field. 蛮好的了，其实蛮好用。Integral domain. Okay. Right. So now we're going to define fraction. Okay, so let's define fraction. Okay, we will finish soon. Definition. Let R be a ring. So first we'll define what is a fraction. So really, fraction is just a symbol. Okay, 一个符号吧。So what symbol here? A slash B or A over B. Okay. And these are an elements inside your R. Okay. And we don't want my B to be 0. We don't want to take denominator to be 0. And we regard anything in R. Wait, let me see. Am I stupid or not? Okay, I think I'm stupid. So such that A, B are elements of R, element in R, and we regard everything in R as what? 这个老师有没有教过你们？啊 We can write R as R over 1. Yeah. 高中哈。Okay, later we'll see why it works. Second, how do we say that two fractions are the same? So whenever we say that two fractions are equivalent, if A1, B2 equals to A2, B1. Okay, cross multiply is the same. Okay, so we denote by A1 over B1 equals to A2 over B2. Okay, so now let's define something. So now so you can see that this equivalent, right? Whenever you see equivalent, you see this equivalent. You need to ask yourself, is this an equivalence relation? Equivalence relations means what? Three property you need to check. The more three property. Reflexivity, symmetric, and transitive. So meaning what? In this case, you translate into what? Whether A over A equals to A over A or not. Sorry, A over B, let's say. A over B equals to A over B or not. And then if A over B equals to C over D, then C over D equals to A over B. Symmetry, right? Transitive, right? If A over B equals to C over D, and then C over D equals to E over F, then A over B equals to E over F. Okay, so check this. Use this cross multiplication. Okay, where's the multiplication? It's here, this one. I use this to check. Okay, so once we have equivalence relation, what can we do? What's follow one equivalence relation? You can partition the set. You use equivalence relation to partition the set. Because once you have equivalence relation, you will form a equivalence classes. Okay, 你就要谁跟你在一起啊，把东西分出来。而且 there's no intersection between these equivalents. OK 吗？可能很伤心啊，你不能够跟另外一个 equivalent class 在一起。But equivalence relation 就是这样，就是要把东西分辨出来。OK, yeah. 可以吗？ OK. Once you have an equivalence relation, you will form equivalent classes. Where there's no intersection between equivalent. So it will partition the set. 事实有时候是很残酷，好不好 ？So let F be the set. 什么？你讲什么？Okay, let F be the set of equivalent classes. Okay, so once we have equivalences, right, we can form equivalent classes of fraction. 对吗？你们老师有没有告诉你们啊？1/2跟2/4是一样的，跟8/4是一样的，12/6是一样的。So these things form a equivalent classes. Okay. Hey, Albert can follow. Can follow what I say? Okay. What I want to say is like 1. 1/2 is the same as 2/4 is the same as 3/6, right? So they form a equivalent classes. Let F be the set of equivalent classes of fractions of elements of an integral domain. So once we start with an integral domain, we can form fraction. Okay, using integral domain. And we'll define, okay, this F is a set. So let me highlight here. So this F is a set of equivalence classes of elements in a integral domain R. Okay. So for example, well, let me give you an example in mind. For example, if I take R equal to Z, what is my F here? So you can see that there are like equivalent classes of half, equivalent classes of 2/3, and so on. Okay, but you know that the equivalent class of 2/3 is equals to the equivalent class of, let's say, 4/6 over 6. Okay, correct or not? Correct. Okay. And what do we want to show here? First thing, we will show that F is actually a field. Okay, it's a field. It's a field. Fraction field. We call a fraction field. Yeah, fraction field. It's a field. So how to take the sum here? Exactly what you do in high school. What you do in rational number here. So how to take sum? A over B plus C over D will be equals to AD plus BC over BD. Okay, how to take product? You just multiply the denominator together and the numerator together. Okay, so you need to check. What do you need to check here? So you need to imagine that you are dealing with equivalent classes. But what do you do here? You just multiply on representative. So meaning what? You need to prove well-definedness. Okay, you need to prove well-definedness. Okay. If there are two representatives for L over D, if there are two representatives of C over D, do they add up to the same thing or not? You need to show. Okay. And other things, should I say it? Yeah, let's say it. So I think this is a good big exercise you can do. Okay, it's a very good exercise to check what. Okay, so maybe I tell you what to check here. Proof sketch. What do you need to check? Well-definedness. Okay, well-definedness. Okay, well-definedness. And then I think that's all. Yeah. Oh, you need to prove a field, right? So you need to check field axiom. Okay, yeah. Yeah, it's a very good exercise. To recall, do you know how to check well-definedness or not? Okay, do you know how to check all the field property? Field property is one more than ring axiom, right? What's the difference between ring axiom and field axiom? All the non-zero element must be a unit. Okay, meaning they have multiplicative inverse. Okay. Right. And then another thing is, what happened to my all integral domain? It is a subring. Okay, it is a subring in F. Okay, but how does my F looks like? My F is a all fraction, but R is just R, right? So how to see R as a fraction here? You will see R as R over 1. Okay, as a subring. So R will sit inside. So R, how to sit inside F here? So how R sit inside F here? Actually, you need to see R as a bunch of R over 1. Such that R is. Okay, and then you prove the subring property. Right. So another thing, one last thing, it's called mapping property. So mapping property says that if R embed as a subring of another field, F prime, so F prime is another field, then what? Then if you write, what did you write? And if you write A over B as AB inverse, also embed F into F prime. Okay, so let me write down what this means. I will draw this picture for you. So let's say we have a R. Okay, we know how it sits inside F prime here. So embed. So here is a. So let me here. So here I'm referring to an injective ring homomorphism. And let's say a phi here. Okay, then R also embed into F. Okay, so just now how to embed into F? I just take R to R over 1. The claim is what? There exists a homomorphism, okay, from F to F prime, such that, let's call this a canonical map. So such that phi equals to capital phi also, such that this diagram can be. Okay. Somehow this says that this fraction field here is the smallest field that R sit inside here. So if R sit inside other field, then you have a map from this smallest field here into other fields. Okay, so somehow this construction here create the smallest field for R to sit inside. Because for any other field that R sit inside, you have a map from this. This is called a fraction field. Fraction field of R. Okay. Yeah. Okay. Yeah. That's all. Okay. No. So this phi here already also tells you, right? So this is sending A over B to AB inverse here. So meaning in this F prime here, you know what's the inverse of B. You know the inverse of B here. Don't know how it is 6, but you have an inverse of B. Just send it to this two product. Okay? Yeah. Because maybe you should imagine 你要想象 maybe the new B inverse is not the 1 over B here. Maybe something else. 不知道是什么. Or it could be different. Okay. Yeah, so you need to check. All right, so let's see what are the fraction field. So what are the fraction field examples? We finish example and then we'll finish the day. So for example, what's the fraction field of Z? So a rational number is a fraction field of Z. So this is the smallest field that Z live in. The smallest fraction field Z live in. What else? Rx. Okay, it's an integral domain here. If R is an integral domain, so what's the fraction field here? Still remember what we call the R round bracket X. You remember what's the R round bracket X here? What is this? Laurent. Laurent, okay. So these are all the equivalent classes of fraction of F over G. Okay. Where Fg live in R adjoint X and G is not 0. Okay. So for example, what are the elements inside here? 1 over X, 1 over X squared plus 1. Okay, so these are the inverses for X and X. Okay. Okay, so if you come to the next lecture, I'll tell you what's the connection of your assignment with future subjects. And I will introduce you, for example, maybe algebraic topology, algebraic geometry, what else? Galois theory, abstract algebra 2, and something like that. Okay, along that line. So how do you proceed after this course? Okay, yeah. And what else we need to talk about next lecture? 还有什么你要我讲吗？最后一个 lecture， 我可以回家准备。如果有机会啊，郝建，真是果然是厦大的学生。郝建 revision lecture 可以再提一提。还有什么 topology？OK， 我们也可以提一下 the general topology。Okay, so I'll see you on Thursday. Huh? 哪一个证明？不说。